Okay, yeah. So thanks for the organizers putting together the workshop and also for properly scheduling my talk afterwards so that I can skip a lot of details. It's very nice to introduce many of them already. So I will continue talking about domain walls, the domain wall day. But I will focus on slightly different aspects of the story, and in particular mix these two words, defects and quality, that typically don't go well together, but we say that in this case they may. So this talk is partially based on two papers, which I wrote with Riccardo Ferreira, Alex Notari, and we always have it here. So there's a series of papers from 21, and then we have a new paper this year. Now, the motivation for this talk and these works, for me, there are two motivations. One is theoretical. So the way I first approached this problem probably was thinking about this word here, quality. So there is a common law, often heard, I'm sure we are also very familiar with it, that global symmetries cannot be exact. This common law is based on several arguments, standard model symmetries, black hole physics. So there are different aspects from which one can approach this statement. However, while the statement is that they cannot be exact, it's not clear how badly violated they would be in a UV theory. So in particular, it's not clear, for example, whether the physics that is responsible for the breaking, that would be responsible for the breaking of the global symmetries, would come in the form of some non-perturbative effect. Non-perturbative, as might be hinted by arguments that have to do with gravity. If you're thinking about gravity as the origin of the statement, and you follow the black hole arguments and so on, you may think that this effect would be non-perturbative, and as such, they would be, let me write it as a potential, so a potential in the sense that it's a term that would break the global symmetry. If it's associated to some non-perturbative physics, then it will come with a scale, m, but also with an exponential suppression, which is for example, the action of some non-perturbative effect. Now, the scale might be, for example, very high if you're thinking of some UV physics. However, if the action is sufficiently large, then even with a very high scale, this term might be totally relevant from the point of view of the phenomenology or cosmology, whatever is more interesting. Now, of course, you can also take the approach instead that, for example, the standard DFT approach, that there will be some higher dimensional operator, some higher dimensional term, and then, some operator dimension n suppressed by a scale with some coefficients. And now, if these coefficients are instead of order 1, then these terms might be much, much more important for phenomenology, cosmology than some exponentially suppressed physics. So at the current time, it's not clear, what these arguments would suggest for how the symmetry should be exactly broken. And so, from a theoretical point of view, it's interesting to understand whether there are systems that are sensitive to what specific source of breaking you would have, in such a way that you may hope to measure actually the breaking of the global symmetry, and then infer from those measurements what the underlying physics is. Now, this overlaps with the observational motivation, which has to do with gravitational waves. So I will show at the end of the talk, I will show some better plots, better than what I can draw. But essentially, since detecting gravitational waves, we have been expanding our reach to the point that today, if you think in terms of the parameter that is typically used by cosmologists, that is omega gravitational waves. That's the relic abundance in gravitational wave today. So it's the energy density in gravitational wave today divided by the critical energy density today. So analog of that matter, relic abundance, and so on. If you think in terms of these parameters, then omega gravitational wave typically also multiplied by h squared, which is just the dimensionless Hubble parameter divided by 100. Then we have, if I put here frequency of the corresponding gravitational waves, we have here a region that is currently probed by LIGO, Virgo, and Cagra. LIGO, Virgo, Cagra. And as you're very familiar with this probes frequency of order 10 hertz, 10 to 100 hertz, let's say, mostly sensitive in this frequency band. And we also have, very interestingly, observations that probe frequency of order 10 to the minus 9 hertz, so nanohertz, and to 10 to the minus 7 hertz. And these are, let me draw it something like this. These are so-called pulsar timing arrays. So these are arrays of radio telescopes that measure pulses of pulsars that are typically very regular, and then by measuring the delay in the time of arrivals, one can infer whether there is a gravitational wave passing through and therefore constrain the relic abundance in gravitational waves. Now, the sensitivity here, there is an important number here that is of order 10 to the minus 6, where we already know that there cannot be a significant contribution to the relic density in gravitational waves because of essentially BBN and CMB physics, which bound the amount of extra relativistic species, in particular gravitational wave, would be contributing to radiation. And this is of order 10 to the minus 6 in this quantity omega gravitational wave h squared. The sensitivity of the detectors are already below this important number. So here for LIGO Virgo 03, I think we are at around 10 to the minus 8. And for PTAs in the nanohertz range, we're already around 10 to the minus 10. We're already probing, let me write it here, 10 to the minus 10. So these amazing numbers, because this is they are fraction of the energy density in the universe today. So we're already probing a very extremely tiny fraction of energy densities in gravitational waves. Now we show at the end of the talk that what's also the future outlook in this plot. So the future, what the future detectors and also the current detectors with the sign sensitivity we reach. So the question for theorists is whether there is anything that particle physics may, that we may discover with gravitational waves, but comes from the early universe, so something that has to do with particle physics. So in this respect, I want to make a brief estimate, a short estimate of the connection between, the frequency of the gravitational waves and the corresponding epoch in the early universe that would be probed by a so-called stochastic background. This is how it's typically referred to when it's of cosmological origins. And also the abundance, so the energy density corresponding to gravitational waves, the energy density of the source in the early universe. So, the typical story is the following. For now, we discuss sources in the early universe that are extended over Hubble length scales and vary on Hubble times. This is, of course, a simplifying assumption. In many cases, this is not true. They vary. They are extended over length scales that are shorter than the Hubble horizon. They vary more rapidly and so on. But this will already give us the right scalings. So in that case, okay, I'm describing here some property of sources and gravitational waves. So the typical frequency of the gravitational waves emitted by a Hubble-sized source will be of order Hubble at the time star at which the source is active, okay? And this, if you redshift to today, you get a frequency of order 10 to the minus 7 hertz for temperatures in the universe of order 1 GeV. Okay. This estimate here assumes a radiation-dominated universe. from the temperature T star to today. Of course, if you have matter-dominated universe, then this estimate would slightly be altered. But I will, for the sake of this talk, I will be always assuming standard cosmology, standard radiation domination. Now, if you want to understand instead the omega gravitational wave, so the amount of gravitational wave that would be emitted by a given source, it's useful to estimate using the standard quadrupole formula. So the power emitted in gravitational waves is proportional to the square of the third derivative of the quadrupole moment. And now if here you put that all the dimensionful quantities are just given by Hubble, so the length scales are Hubble, the time scales are Hubble at the time at which the source is active, then you reach the following conclusion, that the energy density emitted in gravitational waves is just power gravitational waves times, I'm using always, for time I'm using Hubble and for volume as well. Then you get, you just get essentially rho star squared, where this rho is the energy density in the source, divided by h star squared and Planck squared. And this is just, let me write it like this, it's just the energy density of the source divided the energy density of the radiation background at the time star squared times the energy density of the radiation background. Now here, we just redshift today to find that the Redick abundance in gravitational wave squared today is of the order of 5 times 10 to the minus 7. And then it's just proportional to the energy density in the source divided by the energy density in the radiation background at the time at which the source is active, squared. And then there is this epsilon, which I'm leaving as a possible suppression factor, which comes, for example, from the fact that the source is extended on scales smaller than the horizon, or the time scale is not exactly the time scale of the horizon, and so on and so forth. Also, the efficiency factor in a sense of how efficient the source is in producing gravitational waves. And this parameter, this ratio rho source over rho radiation, I will define it as alpha star, following the literature that is typically used using phase transitions. So we see that given this current sensitivity picture that I was trying to draw here, we see that we are sensitive in two frequency ranges currently, which corresponds to temperature of the order of 10 to the 7 to 10 to the 9, probably even a bit larger now, depending on the physics. GeV for LIGO, Virgo Cagra will abbreviate with LDK. So these are the temperature for LDK. And for pulsar timing arrays, instead, as I was saying, we're in the 10 to 100 MeV to 1 GeV, let's say, 10 MeV to 1 GeV temperature range for PTAs. And the corresponding alpha star that we can probe is of the order of essentially 10% for the LDK, and slightly better, something like 5% for PTAs currently. Now, this will dramatically increase in the future when we have new detectors. I will show at the end, but let's say that in the near future, we can expect to probe we can expect to probe sources that make 1 per mil of the energy density of the universe at the time in which they're active. So these are the things that we should be thinking about, whether there are well-motivated sources that can make such large fractions of the energy density of the universe at the time at which they emit gravitational waves. And there are several possibilities. Of course, you're all very familiar with phase transitions. There is reheating, although reheating happens at such high temperatures, possibly that cannot be probed by the interferometers nor PTAs. There are resonant decays, essentially any phenomenon that has a large anisotropy in the energy density, for the polar anisotropy will cause gravitational waves. I want to focus, of course, on defects. So the defects that we heard about from Lyon will also be sourcing gravitational waves, simply because they have this anisotropic distribution, this quadrupolar anisotropy in the energy density, and in particular on domain walls. So here I will significantly simplify the discussion, since Lyon has already been saying a lot. In particular, domain walls, as we heard, form typically whenever there is a spontaneous breaking of a discrete symmetry. We heard about the case of the Z2, so the real scalar case, but I will mostly focus on the axionic case. So in that case, I will mostly focus on that because it's most related to quality of global symmetries, because in that case, indeed, the discrete symmetry arises first from a global symmetry that is a U1 Pechequin symmetry. So you know you have a complex scalar now with the standard Mexican hat. Okay, and at temperatures, at sufficiently high temperatures, you will have a spontaneous breaking of this symmetry, and there will be the formation, the corresponding formation of cosmic strings. As we heard a lot in recent years about axion strings. So they form at the temperature of the order of this parameter d phi. And they correspond indeed to the fact that in the field space, if you want to go from one side to the other, you have to go over the barrier, and that corresponds to a string-like defect that, as I take a loop in space-time, in space, the complex space of this scalar field, of this complex scalar, picks up a 2 pi factor if you think of the angular variable as delta A over P. Okay, so these are cosmic strings forming at this early epoch. Now, we've heard about scaling for domain walls. The cosmic strings also follow a similar behavior in which their energy density, those strings, is just proportional to mu. Mu is the string tension, so it's energy dimension 2. In this case, would be of order v squared. And H is just Hubble at any epoch. So there is a more or less a fixed number of strings per Hubble patch at any epoch, although there is current debate and lots of work on determining precisely how many strings per Hubble patch there are. And apparently there are also some logarithmic deviations from scaling observed in simulations. But that's not so relevant for the talk. So this scales at a to the minus 4, and so it's not dangerous for cosmology. Differently from domain walls, that, as we heard, scale as a to the minus 2. Now, in axial models, what happens is that after you broke the Pechequin symmetry, at some point, some other source of explicit U1 Pechequin breaking will come in, and this is typically due to some non-perturbative effect. Okay, for example, in the case of the QCD axion, this is due to QCD confinement, which generates a potential for the axion, which is temperature dependent, and goes like the axion mass squared, and then there is this v squared over NDW, which is a parameter of the model, and then there is a periodic potential. Okay, you're very familiar with this. Okay, so this new source of explicit U1 Pechequin breaking generates a potential for the axion field, which we can draw like this. Think of these as pi and minus pi. Then there will be, for example, okay, this is just an example, using NDW equals 3. There will be a periodic potential, and in the fundamental axion periodicity, which goes from minus pi to pi in A over V, there will be 3 minima, which are physically distinct. Now, this distance here in field space is what is typically defined as the axion decay constant F, since this is the parameter that determines all the couplings of the axion to matter, essentially. Okay, so this will generically be submultiple of V, where this NDW parameter depends on the microphysics, so it depends on the specific model that you have in mind. And typically, in simple cases, it just counts the number of fermion pairs that are charged under the U1 Page-Shaping symmetry. For example, if you think of the QCD axion, the standard, what's known as the DFSZ scenario, has this number equal to 6. So I should have actually drawn 3 more minima in a fundamental axion periodicity. The case with this scenario, instead, when you have just one fermion pair, then this would be NDW equal 1. But the zoo of axion model is perfectly normal to have that NDW is a number larger than 1. Okay, so what happens in the cosmological evolution, that it's clear from the talk that we heard before, is that once you reach a temperature such that the axion mass becomes comparable to the Hubble rate, the axion field originally is distributed everywhere, essentially in this potential. For example, here, depending on exactly where you are in your Hubble patch. And once the acceleration due to the mass wins over the Hubble friction, then the field will just roll in any one of these minima, depending exactly on where you are in your Hubble patch and on the fluctuations of the field. So you will populate all these 3 minima. Again, this 3 is just an example. In general, you can take any value, any integer value. And so you will form what we heard as what are called domain walls, because you will populate all these values in the same Hubble patch. Okay, so now once this domain will form, it will attach to strings. So that's kind of the interesting part that we were almost going to discuss in the previous talk, is that since there are strings around, by topology, this domain was necessarily have to be attached to the strings. So what will happen, let me sketch a two-dimensional section of the picture. So if you think of this dot as being a string that is outcoming from the plane, you will have these are the original strings that are formed at the Page-Shaping phase transition. By the way, I should say here that this Page-Shaping phase transition doesn't mean the actual, QCD axion Page-Shaping. It can be any U1 global symmetry. I will not discuss specifically the case of the QCD axion for now. Then, as you reach the, so these strings form at a temperature of order F, the axion decay constant. And then as you reach the temperature of the non-perturbative effect that is giving the axion a mass, you will form domain walls that are attached to the strings. And so again, here there are 3 separating 3 minima. And this network, this hybrid network, will also reach a scaling regime, simply because, as we were saying before, the domain walls will very quickly dominate the energy density of this network as they scale more slowly than the energy density in the strings. And so, again, the behavior will just be sigma times h. Now, we've heard this as clearly a domain wall problem. We need an methylation mechanism, and this is where the quality part comes in. Because now, what is often believed as to be a catastrophe, the domain wall problem, actually, if you take into account the fact that global symmetry should not be exact, then you will immediately have a way out of this problem, which is just by having precisely another explicit breaking of the global symmetry. The explicit breaking of the global symmetry in terms of the axion potential would just look like something like this. There will be a Zn preserved in potential, which is the one that I was drawing here. But then in addition, we should take into account the possibility of having another source of breaking, which again, in terms of the axion, would just look like this. Okay, so this delta V is an amplitude of this extra term, which will be related to the microphysics that is leading to the extra breaking of the global symmetry. This N2 is the corresponding parameter which counts the minima in this part of the potential. For simplicity here, I take it to be 1 for the sake of this discussion. And then there will be an offset delta, which is just an offset with respect to the to the minimum of this potential, which is expected in general, since these are two different sources of breaking, they're unrelated, and so why should they be aligned? So that's why I put an offset. Now, if you're thinking of sources of breaking of the global symmetry, it might be useful to rewrite this delta V parameter as some kappa squared times a scale lambda to the fourth. Let me call it B, recalling using the same language that we all used, bias. So there will be a scale here that might be very high scale. Typically, this is the motivation behind the story of breaking of global symmetry. This scale is very high, typically. And kappa B is a suppression factor, which, for example, if you think of a gauge theory, a confining gauge theory, the suppression factor is just the square root of the mass of the lightest fermion divided by the scale lambda B. For example, this is precisely what happens in QCD. QCD instantons are QCD action potential is suppressed by the mass of the upward. If you think about other sources, for example, non-perturbative effects from not from confining gauge theories with fermions, then you would write some exponential suppression, and so on. You can think of other effects. I just wanted to mention some possibilities to relate this delta V to the UV physics. Now, once you have this term, essentially what happens is that it's just what we saw before. So, there will be a breaking of the discrete symmetry. So there will be a gap between the vacua. In particular, only one minimum will remain as the global minimum, and this will have a gap of order delta V. Okay. As we've heard, this creates an acceleration in the network. Also, in the case of a hybrid network, these such terms are enough to make the network disappear. In all the cases that have been studied. Of course, one can imagine an arbitrarily complicated network. Please, let's not think too much about how complicated these things can be. Certainly, they can be very complicated. It's possible, it's at least feasible that a gap would not be enough to annihilate a network that is complicated enough. Okay, but for ZN symmetries with strings attached and the simulations have been performed up to n equals 6, it seems to be established that that the gap is enough to make the network annihilate. Okay, so now the Hubble at which the network annihilates is just given by, as we all told us, by delta V over sigma, simply because the force acting on the domain wall is delta V is a pressure force, and the acceleration is then of order delta V over sigma, which should be compared to the Hubble rate to determine whether it's efficient or not. Now, once this happens, then the network typically annihilates, the wall moves at relativistic speeds, and one is left with the simple network which can annihilate efficiently. Okay, so that's the story in typical axion models. Okay, so I want to give you a flavor of what kind of parameters, translating, this Hubble in terms of axion parameters. Yeah, let me write it here. So, so typically, so if we translate this Hubble in terms of temperature, we will find that the temperature at which the network annihilates parametrically goes like delta V over sigma. And let me rewrite it in the more suggestive way, which contains the basic message of this talk. Okay. It is that this temperature will be proportional to delta V over V. So this delta V over V just quantifies the amount of global symmetry breaking, so delta V over V, where V is the VZN. And the temperature will be proportional to this quantity. So the smaller the breaking of the global symmetry, the smaller the breaking of the symmetry, here now I'm talking about the discrete symmetry if you want, the smaller this quantity, the lower the temperature will be. So in particular, this means that the longer the lifetime of the network will be, as I tune this breaking to be smaller and smaller. And this delta phi is just the distance between the two minima. So for axion model, this is just a okay. And then, of course, b to the 1/4 is the potential. So for axions, translating into masses, one finds temperatures of order 10 to the 8 GeV for very heavy axions, when the mass is of order 10 to the 8 GeV itself. And the breaking of the symmetry is of order 10 to the minus 10. We will understand better why this number is interesting soon. And you notice that with respect to the sensitivity ranges that I was discussing before, this is the sensitivity range of LIGO Virgo-Cagra. Whereas for PPAs, if I want to get here 10 MeV, then the axion mass could be of order GeV with a breaking of the order much smaller than this, of order 10 to the minus 22. So this is for PPAs. Okay. Now, the fraction of the energy density in this network, on the other hand, this is the other parameter that is interesting to compare with the sensitivities of PPA, of gravitational wave observatories. Is of the order that's just given by the energy density in the network at the time of annihilation, which are sigma h star divided h star squared and 1 squared. And this quantity is inversely proportional to this parameter delta V over V. And then there is again the distance between the minima squared. So now we see that indeed this network is more and more relevant as I tune this parameter to be smaller and smaller. So the network is more long-lived, and its energy density compared to the background increases. Of course, in the limit of exact symmetry, of course, the network is it's not decaying, and so you have a domain wall problem. So this is why this contains kind of the first message of the story, that as with gravitational waves, essentially what you can do is you could potentially measure this delta V over V if you were to know the other axion parameters. As these quantities, alpha star and T star, are sensitive precisely to delta V over V. Now, I remind you here also that omega gravitational wave just goes like alpha star squared. Okay, so for axions, again, if I specify these two axions, I will find an order 1% contribution to the energy density of the universe from the source, as the axion decay constant is of order 10 to the 12 GeV, for a variation of order 10 to the minus 10. And I will find the same number, so order 1%. These are the interesting values with current sensitivities for F10 to the 6 GeV, when the variation is much smaller, of order 10 to the minus 22, which is the value I was thinking here. So we see these are both ranges that can be probed by interferometers and by PTAs, and these would be the relevant values of axion decay constant and violation of the symmetries that can already be probed with current data. Yes.
I may have missed it, but there is a bound to just a contribution to theta QCD, just because.
Yeah. Okay. So indeed. So I was not. So this discussion here, as I said at one point, is not specific to the QCD axion. I'm considering any axion model.
For the QCD axion.
Now, indeed, for the QCD axion, as you were saying, there is another parameter, very interesting, another observable that is sensitive to the amount of violation of the global symmetry, and that's just theta QCD. So let me write down the relation between these two parameters. Okay. Okay, so for the QCD axion, delta V over V also determines the size of theta QCD, where this theta, I'm already this is really the physical theta, okay? It's delta V over V, essentially. Then there is, the sign of the offset. Let me take that to the order 1. So then we already know from any dm measurements that this quantity should be less than 10 to the minus 10. And this is indeed what I took 10 to the minus 10 here. And the future looks promising, the near future, in the sense that any dm will go down to, will bound this quantity down to 10 to the minus 12 in the near future. And even proton EDM will go down even more in the near future to one order of magnitude more, I believe, 10 to the minus 13. So that's for QCD axons. For QCD axion, so the one that solves the strong CP problem, there is another exciting observable that is the electric dipole moments of the neutron of the proton. And so you see that this is very interestingly lying close to the sensitivity of detectors. However, and that's when the first one could get a first disappointment from the story, is that for the QCD axion there is another problem that forbids, at least in the simplest case, forbids an observable gravitational wave background. This is due to the fact that the domain wall network, once it decays to axion quanta, right? And the axion quanta can be either stable or unstable. But if they are stable, the results of simulation is that the typical average energy will be of order of the mass, axion mass, and so they are relatively warm, but they will become cold. Okay, so they will just contribute to the cold dark matter abundance. Now, of course, if you have a source, if you want to see a source in gravitational waves, this should be of the order of 1% when it annihilates, and then, of course, if it annihilates in the early universe, it will just overproduce dark matter. Of course, you can play the game of going close enough to matter radiation equality in such a way that this could be the dark matter. You could produce the dark matter out of domain wall decay. Of course, this is not the QCD axion, not the case of QCD axion, but for other ALPS, you could play this game. And you would then, you could maybe hope to see something not at interferometers or pulsar timing arrays, but directly using B modes. But that's a different story. I don't know exactly how close you need to get and how constrained the total scenario is to get gravitational waves as B modes from a string wall network. Now, instead, for heavy axions, which are the ones that I want to consider in this final part, the situation is much better because heavy axions are unstable. So even if they make up, even if the domain wall network makes up a very large fraction of the energy density at the time at which it decays, the resulting axions will also decay, and so they will never overproduce the dark matter. In particular, if you want to get a feeling of the relevant time scale, the typical decay of an axion into, for example, gluons. Here, let's generalize. I'm considering dark gluons or dark photons gauge fields. Is of the order ma cube over fa squared. Then there is a small coefficient in front. Let me not write it down exactly. So you see that for axion masses sufficiently above the MEV, typically, unless F is huge, typically these particles will decay in the early universe before BBN.
Sorry, can I ask you something?
Yes.
The domain wall, after all, they are made of the radial modes, say. No, they're not.
No, the domain wall is made really. No, the strings is made of the radial mode, right? Because the string.
The domain wall is made by
the domain wall is really a configuration of the axion field.
Okay, so I can't play with the cap. Yes. You're right.
Now, so for the QCD axion, let me maybe just finish this discussion by saying that for the QCD axion, in typical models where NDW is larger than 1, one can play this game, and indeed you will find that the constraint from dark matter overproduction is something like this, where you can explain the dark matter even for F of order 10 to the 8 GeV. In this region, the network annihilates at temperature slightly above the MEV, And yes, and the dark matter is produced by domain walls dominantly, whereas here the bound is set by the standard misalignment mechanism or the string decay contribution. Okay, yeah, this I just wanted to conclude the stability, the part in which it's stable. Now, for actions that are stable, that decay, you have constraints also from delta N, because if they decay into light species, into radiation, this delta N will be bound from CMB and BAO to be less than 0.3 at 2 sigma. From BBN, slightly worse bound. And this will translate into a bound on alpha star, which is depending exactly. So it's of order one, let's say, it's very close to the sensitivity of current constraints if I translate this bound into an alpha star, into a bound on alpha star. This is if they decay into dark relativistic species, but of course they could decay, one could conceive a model where they decay to standard model. If they decay to a standard model, then this bound does not apply. However, the bound that will apply is that the temperature of annihilation should then be above 3 MeV, let's say, that is the temperature of BDN, because if they decay at BDN or slightly afterwards, even if they make a small fraction of the energy density of the universe, since the mass of the father or mother is very large, then they will inject highly energetic photons in the plasma, and this is ruled out by BDN. Okay, so that's the constraints. Now, the things that I will quickly show on the slides in the remaining part is constraints is the detection outlook at LIGO and at PTAs in detail. For models that are general axion model, but in particular we consider also heavy QCD axion models, which are motivated again by quality, because you see this extra breaking of the Pechetian symmetry is typically also thought as a problem in QCD axion models, because as you know, this would induce, if it's large enough, it would induce a theta, which is larger than the one that we already know. It should be less than 10 to the minus 10. So the idea in these heavy QCD axion models is that you see, the problem is extreme. The so-called quality problem is extreme because V is typically VQCD, is the QCD axion potential, and it's very, very small compared to any UV scale. This delta V, let me write it better here. This delta V, as I was saying, is some UV physics, for example, and then here there would be the amplitude of the QCD axion potential. That is just kappa QCD times lambda QCD to the fourth. That is just the ratio of the upward mass to lambda QCD. So you see, here there is a problem because if I consider lambda B to be some well-motivated UV scale, for example, let's say GAT, 10 to the 16 GeV, I have to compare this with 100 MeV, then of course here we get a huge number. And this will mean that I have to tune this kappa B in order for this quantity to be less than 10 to the minus 10. I need to tune this kappa B to be a very small number of the order of lambda QCD over lambda B to the fourth. Now put here 10 to the 16. You see this will be 10 to the 16 to the 10 to the 17 to the fourth power. And explaining why this parameter should be so small is challenging if you're thinking, especially for example, of higher dimensional operator corrections. If you think of exponential suppression, it will still require a sufficiently large action of the order of 200 or something. So that's the quality problem. Now, a possible way to address this is heavy QCD axion models, of which we also have some experts here in the audience. I will not cite in detail all the works. There is a lot of work in recent years on this. These models essentially propose to replace the QCD axion scale in this estimate by some other scale, lambda h, which is much, much heavier than lambda QCD. So the idea of these models is just that the axion could get another correction, another potential of with an amplitude which is much larger than the QCD one. Of course, this should be very finely aligned, perfectly aligned, essentially with the QCD axion potential. And this can be done invoking invoking, for example, small instantons or extra Z2 symmetries to relate to dark sectors and so on. So there are very interesting works in the literature on it. Okay, so last 5 minutes, I just wanted to show some slides, some plots. I'm sorry that I'm taking a bit too long. So this is sort of the general picture and motivation behind the interest in domain walls and gravitational waves. And now I will show the analysis that we did with Riccardo, Alessio, Uriol for LIGO. And then a very recent analysis that we did using, for the first time, the actual pulsar timing array data, the exciting data that are out now with nanograph, PPTA, EPTA data. We did a search in the data sets for these objects. Okay, yeah, so this is. Okay, so this is what I wanted to show at the beginning. These are the sensitivities that we currently have. And this is how the future looks. We will have, again, much more interferometers with much higher, with much better sensitivities, down even to 10 to the minus 17 in the relative abundance. Now, in this paper from 2021, we looked then at the outlook for LIGO Virgo Kagra. So here on the y-axis, I have mu b over lambda h, where lambda h is this higher scale. So I'm considering a heavy QCD axion here with a scale lambda h that is much larger than the QCD scale. And the mu b is just delta b to the 1/4, okay? So mu b is just delta b to the 1/4. So it's the scale of the breaking term. And here you can see the thresholds for detectable neutron electric dipole moment and proton electric dipole moment, which correspond to theta of 10 to the minus 13 and 10 to the minus 12. So you see that in these models, which have QCD axions with a very high lambda h of order 10 to the 10 GeV here, you get a signal at LIGO Virgo Kagra from the domain wall annihilations, and correlated with the detectable electric dipole moments for, as I said, for axion decay constants of order 10 to the 10 to 10 to the 12 GeV. This is, instead, if you also look at the sensitivities of future interferometers, but you fix the amount of symmetry violation to something that is observable at the neutron electric dipole moment experiment. So everything that you see here in this parameter space will be probed also by neutron electric dipole moment experiments. And then you see how the future interferometers will reach much deeper in the parameter space of the heavy QCD axial models.
Sorry, can I ask you something? So the temperatures here, so how you can be sure that you, so typically in these models there is a lot of structure, no? Like in this heavy QCD axial.
Yes. So structure, you mean in the particle physics model?
Yeah, so the worry is that when you heat it up, it will, you know, this effect, you know, this picture that you have, that the only effect of these models is really to crank up the axial mass.
Yes.
Is not very robust when you at high temperature.
You mean less? Sorry, maybe rather than temperature, talking about scale. You know, in the model, forget about the universe, but in the model, as you raise the scale of these models, you think that they will be more and more sensitive.
I'm just saying these gravitational waves are produced at a given temperature.
Yes, in this case, it's of course, if you're looking here, it's very high. Yes.
Yeah, which I need to compare with the dynamics that is responsible for generating your axial mass. And this might sensibly affect your prediction. You see what I'm saying?
No, the dynamics. So the only way to affect the gravitational wave prediction is if there is, for example, a phase of matter domination. Rather than radiation domination. In that case, you get a different plot that we have in the paper.
Or like multiple phase. You know, there are like this model. You know, this model typically you have to embed SU3 in like a larger gauge group. There are going to be multiple phase transition. You cross. You know, there is a lot of.
So you're imagining some non-standard cosmology, like you know, a phase of.
I mean, it's very likely. That's what I'm. unfortunately, that's what I'm trying.
So in order to affect the gravitational waves, again, you need to affect the expansion of the universe, right? So you either need matter domination. This will change the picture, but it will not kill the outlook. There will still be a region that can be explored. We have it in the paper. I'm not showing it here. If you're thinking of supercooling phase transitions, I don't think these are typical in this.
No, I'm just thinking about another phase transition. That is
another phase transition will not affect this because it will be another source of gravitational waves. That, of course, then you need to figure out how to properly subtract these things in the detectors. If you see many signals at different frequencies. So here I'm focusing only on this signal.
No, but yeah, it was just like very. So in this plot, there is certainly a region in which instead you don't care about this comment, no? It is for temperature that are well below this scale of lambda h, no? Do I understand correctly or no?
So this in this plot, in all of this plot, the annihilation occurs always much below lambda h. This is what you're asking. Because you form the domain wall at the scale, right, at that scale, and then it annihilates at some point afterwards. So
okay, yeah. So the only thing that you can modify is the abundance of the domain walls at the time of annihilation. UV physics can only affect this.
Yeah.
Right?
If you want, yes. If you have some modification of the background expansion, then you could affect certainly the gravitational wave propagation, that's for sure. Now, the evolution of the domain walls, it has to be something very strong because, you know, the domain walls dilute slower than anything else. So, except for, you know, if you have some late inflationary phase.
So. Phase transition will be at higher frequencies, no?
Yeah.
If coming from the embedding into the model, no?
Well, at higher frequency, at the frequency dictated by lambda h.
Whatever, but higher than the frequencies at which the domain walls dominate. No?
Yeah,
that's for sure.
Yeah.
So this you can have a bump. Yeah, you can.
No. I was just. It was mostly to understand. So it's just that. So the only thing that the UV can do is to dilute essentially this domain wall abundance, but nothing else. You see.
Yeah, dilute again if it leads to a modification of the background expansion, so a non-standard cosmology. Yes, that could happen. Even the domain walls could do that. For example, if the domain walls decay into axions, but the decay rate of this axion is not efficient enough for them to annihilate immediately, right? Then this cold axion can lead to a phase of matter domination for a while, and then they eventually decay. That can happen. So sure. So there is a modification, another version of this plot, including matter domination. Actually, sorry, this already includes the matter. In this plot, you see that these lines are cut like this. There are some regions in which there's a different slope. This already includes the matter domination from the axions produced by the domain wall decay. So this is already taken into account into this plot. But there could be other, you know, for example, if it's another confining that sector, there could be some baryon, some mesons that I'm not taking into account here because that's more model dependent. Yeah. Now, so more recently we looked at pulsar timing array data. I don't have time, unfortunately, to recall these beautiful results from pulsar timing arrays, which hopefully are a true hint of gravitational waves, of the first detection of the stochastic gravitational wave background at nanohertz frequencies. This is the money plot from the most recent pulsar timing array data release. This is from the International Pulsar Timing Array. You see that currently there is strong evidence for a common process, but not yet complete evidence of gravitational waves, since the Helling-Sounds quadrupolar correlations have not been detected to date. But the Nanograv collaboration expects, if this is indeed gravitational waves, to be able to confirm this in the next few years. These are broadly consistent results from all pulsar timing arrays. And of course, there is an astrophysics signal, which is a possible candidate to explain the excess. This is just the collection of supermassive black hole binaries of order 10 to the 6, 10 to the 5 solar masses. These are huge and they're very far away from merging. But it's very important at this point, since we possibly have a detection, and we could have it even if this is not a detection, we could have it in the very near future, to consider the implications for particle physics. So here we did a Bayesian search in the data from Nanograph. This is Nanograph 12.5-year datasets, and this is the IPTA data release 2 for domain walls. So these are the gravitational waves produced by domain walls, and the relevant parameters when the walls decay to dark radiation are delta and F and the temperature of annihilation. So you can see here, these are the region compatible at 2 sigma with the current data. So the region that can explain the current excess in terms of this parameter, and instead, for the case of decaying to standard model, this is the situation where now I chose to parameterize here in terms of the relative abundance of the domain wall network at the time of annihilation. So you see, as promised, this is of order 5 to 10%. And as promised, from dark radiation, there are strong constraints already on the possible interpretation in terms of new physics from CMB. Here I am recapping what the spectrum would be. This is spectrum, a spectrum for a general stochastic background can be parameterized as this, with a slope at high frequencies, which is given by this parameter beta, and at the small frequencies is given by 3, typically, due to causality. And this is how a typical spectrum looks like compared to the data points, although don't quote me on this, these are not exactly data points from the pulsar timing arrays. So these are the best fits values that we found for domain walls. So the dashed lines are the typical, the behavior inferred from simulation is that there is this rise as frequency cube. This is just for causality. And then at frequencies beyond the peak, there is a linear decrease 1 over frequency at frequencies larger than the peak. But we also explored the slightly different width and slopes at high frequency, as might be motivated by other models or by more sophisticated axion models. So you see that the interracial pulsar timing array would prefer a signal that has a peak right in between 10 to the minus 9 and 10 to the minus 8 hertz, whereas the signal from the data from Nanograph currently prefers something that we speak even at frequencies below the nanohertz. Although this is, a very mild preference, so it's not, we're not talking about many sigmas in terms of where to place the capability. This is, we also did the exercise of including a stochastic background from supermassive black hole binaries. This is what will become essential, since we know that we expect a stochastic background with amplitude A GWB from astrophysics. And you see that in this case, when you include both the astrophysics background and the new physics background, you see that the current data are not able to choose between the two essentially. And so it will become crucial to better establish what the new physics spectrum really is in order for the future data to be able to distinguish. This is just the results in terms of the scales. So in terms of the tensional domain walls that can explain the current signal, if this is indeed due to gravitational waves, is over the order of between 10 to the 4 and 10 to the 5 GeV. And this is something that is very interesting for models with new heavy scalars, as we know, possibly also related to the weak scale. And the scale of the breaking term instead is of order just below the QCD scale. So this is very interesting if one thinks of axion models, because then one could possibly think of using QCD itself as a source of domain wall annihilation. And this is the parameter space with constraints that we obtain for a heavy axion coupled to QCD. So you see this is the mass, as promised, is in the range of 1 GeV to even 1 TeV. These are the regions at 2 sigma compatible with the current excess in Nanograph and IPTA. And these are other regions which will be probed by colliders and lab experiments. So you see that there is also significant overlap in part of this parameter space. All right, yeah, that's it. I'm sorry that it took way too long. Thanks for your patience.
Then if you're hungry, will leave the questions for lunch.
Yeah.
Okay.
Okay. Thanks.